Hey guys, welcome back to Bottom-Up Chem. In this video, we're going to be starting Unit 15, specifically Born-Haber cycles. It's important that as we begin these, we bear in mind that these are just an extension of other Hess's cycles, and in that way, we're not really doing anything new. Before we get started, have a go at this question using average bond enthalpies that are given in the table at the top right hand corner. Pause the video to have a go at it. Okay, so going through this question, first of all, we want to draw out the Lewis structures so that we don't miss out any bonds. So we've got CH4, C single bond Cl, and then we've got CH3Cl, so replacing one of the hydrogens for a Cl, and then a HCl bond. So remember that delta H is going to be equal to the sum of the bonds broken minus the sum of the bonds formed. So we're going to total up the bonds broken, which is going to be 4 times the CH bond, which is 414, plus 1 times 242. And from that, we're going to subtract 3 times 414 for all the CH bonds, plus 1 times 324 for the CCl bond, plus 1431 bond. That leaves us 1898 minus 1997, which is minus 99 kilojoules per mole. Okay, turning our attention to lattice enthalpy. Firstly, what is lattice enthalpy? So lattice enthalpy is the enthalpy change when 1 mole of a solid ionic crystal is converted into the gaseous ions that make it up. Now, you'll want to be careful if you're looking elsewhere online here, as many other sources actually define this lattice enthalpy as in the other direction. And the IB does it in this direction. And I think the main reason for that is it kind of ends up being analogous to a bond strength for ionic bonds in the way we're looking at it here. And this is very useful because enthalpy of formation cannot be calculated for ionic compounds. So what we can do is we can use lattice enthalpy and a little bit of Hess's law to be able to calculate indirectly the enthalpy change of formation for an ionic compound, and we do this using Born-Haber cycles. So before we do that, let's look at 2 main factors that affect the value of lattice enthalpy. The first factor is ion charge, and the second factor is ion size, and these two both have an effect. So if we think about ion charge, the larger the charge of an ion, the more it's going to pull other ions towards it, obviously. So increasing ion charge increases the force of attraction between the 2 ions, and this of course then increases the value of lattice enthalpy because we have a stronger attraction. Ion size works kind of in the opposite way. If we think about an ion with the same charge, so all 1 charge here, as we increase the size, we decrease the charge density. That's the charge per unit volume of an ion as we increase the radius. So we would decrease the force of attraction as the ions get larger, and that would decrease lattice enthalpy, or inversely, the smaller the ion, the larger the lattice enthalpy. So when either of these are changed, we end up changing the lattice enthalpy. And now that we know this, we're able to use it to make educated guesses about comparative sizes of lattice enthalpy, just based on comparing the ion charge and the ion size of 2 different compounds. Okay, so now we've been introduced to lattice enthalpy, let's have a look at constructing a Born-Haber cycle. So remember, a Born-Haber cycle allows us to find enthalpy changes for ionic compounds. And usually this focuses around lattice enthalpy and enthalpy of formation. Now, the way we construct these, and you can construct them slightly differently, and some questions will be constructed slightly differently to this diagram, but I'm going to do this because I think it illustrates it the best. So we've got energy changes around this cycle, and we're going to start with an ionic solid at the bottom. And then we're going to go through the certain steps that will allow us to utilize our understanding of lattice enthalpy, but we're going to need to go step by step and include each of the energy changes and, just as importantly, where to find those energy changes in the data booklet and how to use and write an equation for each step. So first things first, for an ionic solid, let's call it MX solid, we're going to put that at the bottom. We're then going to use the enthalpy of formation, although we could also be finding the enthalpy of formation. So we know by the definition that enthalpy of formation is turning the elements in their standard states into a compound. So we can put the element, the metal, which in this case will be a solid, plus half the moles of the non-metal gas. The reason I've got half here is because we only have MX with one X atom. If we had MX2, then we would use just the plain 1 mole of the diatomic non-metal gas. So we want to find an alternate route up and all the way around using lattice enthalpy. So if we want to use lattice enthalpy, we need to find all of the enthalpies that are going to get the metal to an ionized state and a gas, and the non-metal also to an ionized atomized state as a gas. So I'm going to go first with the atomization of the metal, and that is going to leave us with M gas plus half X2 gas. Then I'm going to do the same with X2. Now, even though I've got half X2, that's indicating that I have half a mole of X bonded to X. So I still need to atomize that and get X all by itself. Now I have both as just individual atomized elements, I need to get the ions. So over here, I'm going to take the ionization energy of the metal. Now, if this is doubly charged, you'll obviously take the first and the second or third, depending on which metal you have, but we're just going to do this as a 1+ charge here, plus obviously X gas remaining the same for the moment. Lastly, I get round to the place where I'm meant to have 2 ions. So I need to now ionize my X, and instead of taking the ionization energy, we're going to have to take the electron affinity again. If it's a multiply charged ion, then you will take the first and second or third. So now we have M plus gas plus X minus gas. So the change that is left, that's going from ionic solid to the gaseous ions, is the aforementioned lattice enthalpy, which we can say is kind of analogous to the bond energy of an ionic compound. Let's have a look at an example then, and where we can get these values from if they're not given in the question. So here we're calculating the lattice enthalpy of NaCl. Here I'm going to give us the enthalpy of atomization for Na, and I'm also going to give us the enthalpy of formation for NaCl. So we're going to start at the bottom, which is going to be our solid ionic salt, which is going to be NaCl solid. And of course, that on the left, we've got the enthalpy of formation, which is going to be the elements in their standard states. And we've been given that value, which is minus 411 kilojoules per mole. Now we need the enthalpy of atomization I'm going to do for Na next, which gives us Na gas plus half Cl2 gas. And that's plus 108 is already given to us. Then we're going to atomize Cl because we only want Cl atoms by themselves, not bonded. If we go to table 11, then we have the average bond energies. So if we look at Cl as shown on that table, then we can assume half of the Cl bond would be equivalent to the atomization for 1 mole of gaseous chlorine atoms. And obviously the value itself would be the value for 2 moles of chlorine atoms, but we only need 1 here, so we're going to half that value. That leaves us with Na gas plus Cl gas. And we're ready to start ionizing. So here we're going to look to table 8 in the data booklet, and we'll find the first ionization energy for Na, and that shows us it's 496 kilojoules per mole. So that leaves us Na plus gas plus Cl minus gas. Now, of course, we want to ionize the Cl. However, that is a non-metal, so we're going to use the electron affinity from the same table 8, and the electron affinity for Cl is minus 349 kilojoules per mole, which leaves us with Na plus gas plus Cl minus gas. And now we're ready to put this all together to solve for the lattice enthalpy using Hess's law. So you'll remember that Hess's law states that whichever route we take, all the energy changes will be equal. So we can sum total all of these energy changes following this arrow, and that will give us the value for lattice enthalpy. Just remember that if we go against an arrow, just like with the simple thermochemical cycles, we're going to flip the sign, and if we go with an arrow, then we're going to add it. So we get lattice enthalpy equals plus 411 for the enthalpy of formation, plus 108, plus 121, plus 496, and minus 349, which equals plus 787 kilojoules per mole for the lattice enthalpy. And if we look at table 18, which tells us the lattice enthalpy, we see that we have a 790 kilojoule per mole lattice enthalpy, which is pretty close, and considering we've used average values for our average bond enthalpy, that's not too far away. We can even do the exact same process with finding the enthalpy of formation. So let's do that for MgCl2. I'll give us the enthalpy of atomization of magnesium is 148 kilojoules per mole, and the second ionization energy of magnesium isn't given to us on table 8, which is plus 1451 kilojoules per mole. So we set this up in the same way with our ionic solid at the bottom, MgCl2 solid, and that's going to give us magnesium solid and Cl2 gas. Remember, we're not halving it here because we require 2 atoms of Cl2 in the final. Then we're going to atomize magnesium using the value that we're given, which is 148. Atomize Cl, and remember, we're going to want 2 moles of chlorine gas. So on table 11, the average bond enthalpy, we're going to take the total 242 kilojoules per mole because we're going to break one of those bonds and give us 2 moles of Cl. Then we're going to ionize magnesium. So we can take the first ionization energy from table 8, but we're also going to need to use the second ionization energy, which I gave us at the top, which is plus 1451. So we're going to need to combine both the first and second ionization energies to be able to get the overall energy, which is plus 738 and also plus 1451. Then lastly, we're going to need to ionize our chlorine too, and remember, it's 2Cl going to 2Cl minus, so we're going to use table 8 to get the first electron affinity of chlorine, but we're going to multiply that value by 2 as we've got 2 moles of Cl minus to be produced, which is minus 349 multiplied by 2. Now for the lattice enthalpy, we can go to table 18 and get the value for the lattice enthalpy of MgCl2, which is plus 2540. So just as before, we can use Hess's law to create an equation to solve for the enthalpy of formation. So all we need to do is take all of the values as we go round the cycle. So the enthalpy of formation is going to equals plus 148 plus 242 plus 738 plus 1451. And then coming down the other side, we've got plus 2 times minus 349 and minus 2540. Watch, because we're going against the arrow of the lattice enthalpy, which gives us an enthalpy of formation of minus 659 kilojoules per mole, and the actual is close to minus 642 kilojoules per mole. And of course, this is to be expected as there will be a slight error because we've used average values. Okay, time for a couple of questions then. Okay, first question, write an equation to represent the lattice enthalpy of LiBr. Pause the video and have a go. Pop 'em up! remembering that we're going to express a lattice enthalpy as the enthalpy change associated with the transformation of the solid crystal, in this case LiBr, into its gaseous ions, which would be Li plus gas plus Br minus gas. Okay, probably going to take you a few more minutes this one, but use the template I've given here to construct a Born-Haber cycle for LiBr, the compound, and find the enthalpy of formation using data tables 8, 11, and 18. Take your time, pause the video. Pop them up! So filling in the rest of this cycle, we know that it will be Li solid plus half Br2 gas, and that, if we atomize the lithium, will give us lithium gas plus half Br2 gas. Then if we atomize the bromine, which we can get from half of the Br enthalpy on the table 11 data table, we get Li gas plus Br gas. Now if we want to start ionizing these, we can go to table 8. We've got the first ionization energy of lithium, which the data table shows us is plus 520 kilojoules per mole, which gives us lithium plus gas plus Br minus. Taking the electron affinity from table 8 for Br minus, we get minus 325 kilojoules per mole, and then we can go to table 18 to get the value of the lattice enthalpy for LiBr, and that shows us that we have plus 820 kilojoules per mole, and then we can put all of this together and solve for the enthalpy of formation. So remember, because of Hess's law, we can just sum them all the way around the cycle. So I'll start with the atomization, plus 161 plus half of 193, which is 96.5, plus 520, plus negative 325, which is just negative 325, and minus 820, gives us a value of minus 367.5 kilojoules. If we look at the actual value, we get minus 351. Again, that slight deviation is expected due to our use of average values. Awesome. So using what we've learned now, we can have a look at the enthalpy of solution. So the enthalpy of solution is the enthalpy change when 1 mole of an ionic crystal substance is dissolved in excess water. And when I say excess, I mean technically this should be kind of an infinitely large amount of water, but it's just a really, really large excess at standard temperature and pressure. So an example of this would be NaCl goes to Na plus aqueous plus Cl minus aqueous. Now, if we don't know this value, we are able to use the lattice enthalpy to construct a simple Hess's cycle to solve for it. We know that the lattice enthalpy is NaCl goes to Na plus gas plus Cl minus gas, and the transition from the gaseous ions to the aqueous ions is simply the enthalpy of hydration, which is the enthalpy change when 1 mole of a gaseous ion is dissolved in excess water. Again, the same kind of very large excess as before. These values are given in the data booklet, so we can then solve for the enthalpy of solution. We know that the enthalpy of solution is going to be equals to going down and then up this thermochemical cycle, so we get the lattice enthalpy plus the enthalpy of hydration of the positive ion and the negative ion combined give us the enthalpy of solution. So solving very quickly for NaCl, we can use table 18 for the lattice enthalpy, and we can use table 20 for the enthalpies of hydration of Na plus and Cl minus respectively. So on table 18, it shows us that the lattice enthalpy of NaCl is plus 790, and on table 20, it shows us that the enthalpy of hydration of the chlorine is minus 359, and the enthalpy of hydration of sodium is minus 242. And we can resolve for that and we get plus 7 kilojoules per mole. These values tend not to be incredibly large, as it's just the enthalpy dissolving in water, and remember, water is a polar solvent. The actual value on table 19 shows us 3.88 kilojoules per mole. Again, because we've used some average values, we don't have a perfect estimate. Okay, a couple of questions to finish us up on that then. First question, define hydration enthalpy. Pause the video and give it a go. Pop 'em up! Of course, the hydration enthalpy is the enthalpy change associated when 1 mole of gaseous ions are dissolved in excess water. Next question, calculate the enthalpy of solution of magnesium chloride using table 18 and 20, using the method we did before. Pause the video and have a go at this. Pop them up. So of course, using the same thermochemical cycle as we used before, we're going to have magnesium chloride solid goes to magnesium 2 plus aqueous plus 2 Cl minus. So we can use table 18 to get the lattice enthalpy, which is plus 2540, which is going to leave us with magnesium 2 plus gas and 2 Cl minus gas. And then we have to account for the enthalpy of hydration values, which we can get from table 20. So we find that Mg2 plus is minus 1963 and Cl minus is minus 359. Of course, we're going to use 2 moles of the 359. So we get plus 2450 plus minus 1963 plus 2 times minus 359 gives us an overall value for the enthalpy of solution of minus 141 kilojoules per mole. We can check that against a couple of online sources, and I found that to be about minus 127 kilojoules per mole. And again, that slight deviation is going to be caused by our use of average values. Okay, no practical work on this, but there is a worksheet with some scaffolding to help you structure these and practice. Thanks again for joining me, guys. Don't forget to like, subscribe, hit the bell icon, and as always, practice makes slightly better.